I've been working on black holes recently, something I hadn't even begun exploring the last time we spoke. What drew me in wasn't just the mystery, but how much progress has been made in such a short time. At the center of our galaxy lies a black hole so quiet, so starved of matter, that astronomers once believed it was incapable of meaningful activity. And yet, in a single unexpected moment, the James Webb Space Telescope captured something no telescope had ever seen before: a mid-infrared flare erupting from Sagittarius A star, a flare that by all conventional expectations should not exist. So what triggered this impossible burst of light? How did Webb manage to detect it? And what does it mean for the future of black hole science? The silent heart of the galaxy. At the center of the Milky Way, roughly 26,000 light-years from Earth, sits an object that refuses to behave like a typical supermassive black hole. Known as Sagittarius A, often abbreviated Centaur-A statistics, it contains the mass of about 4.3 million suns, compressed into a region smaller than the orbit of Mercury. It is the gravitational anchor of our entire galaxy. Every star, every cloud of gas, every spiral arm ultimately orbits around it. And yet, Sagittarius A star is remarkably quiet. Unlike the supermassive black holes at the centers of active galaxies, objects that violently consume matter and unleash enormous jets of energy, SGR-ASG barely feeds at all. It is surrounded by a thin, hot, rotating cloud of gas and dust known as an accretion flow, but most of that material never reaches the event horizon. Instead, it orbits, heats up, cools down, and gradually drifts away. Because of this extremely low feeding rate, Sagittarius A stick emits very little light. To most telescopes, it appears faint, almost dormant. But every so often, typically a few times per day, that calm is broken. For brief moments, sometimes lasting only minutes, the region around the black hole suddenly brightens dramatically in infrared light. These events, known as flares, are thought to be caused by electrons accelerated to near the speed of light by intense magnetic fields near the event horizon. Until recently, however, scientists lacked the data needed to truly understand these flares. The missing piece of the spectrum: astronomers had observed Sagittarius A star in radio wavelengths. They had detected flares in the near-infrared. But between those two regions of the spectrum lay a critical gap: the mid-infrared. Earth's atmosphere blocks almost all mid-infrared radiation. From the ground, this part of the spectrum is essentially invisible, and that blind spot mattered. Mid-infrared light carries vital information about how energetic electrons cool, how magnetic fields evolve, and how energy is redistributed near the edge of a black hole. Without it, scientists could only infer what was happening, never directly observe it. For decades, this missing data left a hole in black hole physics. The only way to fill it was to go to space, a telescope built to see the invisible live. The James Webb Space Telescope was designed precisely to overcome these limitations. Orbiting nearly 1 million miles from Earth at the Sun-Earth L2 point, Webb operates in an environment of extraordinary thermal stability. Shielded by a massive 5-layer sun shield, the telescope cools to temperatures low enough that its own heat does not overwhelm the faint infrared signals it is designed to detect. This allows Webb's mid-infrared instrument, MARIE, to achieve sensitivity unmatched by any previous observatory. But sensitivity alone wasn't enough. What truly transformed black hole observations was MARIE's spectroscopic capability. Instead of measuring brightness at a single wavelength, it splits incoming light into many mid-infrared wavelengths simultaneously. This is crucial because a flare from Sagittarius A coming is not static. It evolves rapidly, brightening, fading, and changing character as electrons gain and lose energy. Each wavelength responds differently during this process. To understand the physics, astronomers must watch the flare unfold across the spectrum in real time. Before Webb, that was impossible. Near-infrared telescopes could see the flares, but only their outer layers. Radio arrays detected slower variability, but missed the sharp bursts. The mid-infrared, the region that connects these processes, remained completely hidden. When Webb turned its gold-coated mirrors toward the galactic center, it didn't just capture an image, it opened a window that had never existed before. And through that window, for the first time in history, a mid-infrared flare from Sagittarius A star emerged from the darkness, the flare that shouldn't exist. There is a fundamental truth at the heart of black hole physics. A black hole itself cannot emit light. Once matter or radiation crosses the event horizon, it is lost forever. So if the black hole is dark, what exactly is producing these flashes? The answer lies just outside the event horizon. Sagittarius A is surrounded by a turbulent, magnetized flow of gas and dust. Most of this material never falls in. Instead, it moves chaotically, colliding, stretching, and twisting as powerful magnetic fields contort it into complex structures. Under normal conditions, this environment glows faintly in infrared light and remains relatively stable. That stability is what makes Sagittarius A star appear so quiet. But occasionally, something changes. A knot of gas compresses. Magnetic field lines reconnect. Electrons are suddenly accelerated to extreme energies. In those moments, the calm environment near the event horizon erupts, producing a flare that briefly lights up the heart of the Milky Way. And thanks to the James Webb Space Telescope, we are finally seeing these events in their full complexity. Magnetic field lines reconnect. Electrons are suddenly accelerated to speeds approaching that of light. And when that happens, the region just outside the black hole erupts in a brief but powerful burst of energy. This is the flare. It is not light emitted by the black hole itself, but an indirect signal. Radiation produced by matter interacting with intense magnetic fields just outside the event horizon. These flares typically rise and fall over timescales ranging from minutes to hours. In near-infrared wavelengths alone, astronomers have observed hundreds of them, each offering small clues about the extreme physics at work. But those observations always came with major limitations. Near-infrared data could capture the initial surge in brightness, revealing the moment when electrons are first accelerated. Radio observations could track slower, more distant changes as energy spreads outward. But the crucial middle phase, the transition between these two regimes, was missing. That missing link lies in the mid-infrared, the missing chapter in the story. The mid-infrared occupies a critical position in the electromagnetic spectrum. It is where the fastest, hottest electrons begin to cool, and where energy transitions from its most extreme state into something more stable and measurable. This region holds the key to understanding how flares evolve after their explosive birth. Until the James Webb Space Telescope, no one had ever observed this phase directly. For decades, astronomers studying Sagittarius A ran into the same frustrating wall. They could observe the flare's sudden appearance in near-infrared light. They could track its later evolution in radio waves. But the mid-infrared, the region that connects these two processes, was completely inaccessible. Earth's atmosphere absorbs nearly all mid-infrared radiation. Even the most advanced ground-based observatories are blind to it. As a result, scientists were forced to rely on assumptions. They estimated how quickly electrons lost energy, inferred the strength of magnetic fields, and guessed how much material was involved. These estimates often carried large uncertainties. It was like trying to understand a story with an entire chapter missing. That missing chapter wasn't just inconvenient, it prevented theories from being tested properly. Models of magnetic reconnection, particle acceleration, energy transfer, and electron cooling all depend on knowing how a flare behaves across multiple wavelengths. Near-infrared alone wasn't enough. Radio alone wasn't enough. Only the mid-infrared could reveal whether the predicted physics, especially synchrotron cooling, was actually happening. Webb opens the hidden window. The James Webb Space Telescope changed that instantly. With its mid-infrared instrument, Webb didn't just glimpse the missing region, it mapped it in detail. During the flare, Webb observed Sagittarius A style simultaneously across 4 distinct mid-infrared wavelengths, creating the first complete spectral fingerprint of a black hole flare. For the first time, astronomers could watch energy move smoothly from higher to lower frequencies. They could see how brightness evolved across the entire mid-infrared range, and they could finally test decades-old predictions against real data. Electrons on the edge of a gravity well too. Understand what Webb actually saw, we have to look closely at the particles driving the flare. Near Sagittarius A, gravity is so extreme that space and time themselves are heavily warped. Gas swirls at enormous speeds. Magnetic fields twist, snap, and reconnect. In this chaotic environment, electrons don't simply drift. They are violently accelerated to nearly the speed of light. As these fast-moving electrons spiral around magnetic field lines, they emit synchrotron radiation. This same process powers the colossal radio jets of distant galaxies and the glowing remnants of supernova explosions. But around Sagittarius A, it unfolds on a much smaller scale, within a region only a few Schwarzschild radii from the event horizon. Synchrotron radiation is exquisitely sensitive to two things: the energy of the electrons and the strength of the magnetic fields they encounter. Near-infrared observations reveal the highest energy electrons, freshly accelerated and radiating intensely. But those electrons cool rapidly. As they lose energy, their emission shifts toward longer wavelengths. That shift is exactly what the mid-infrared captures. It is the zone where cooling becomes visible. Before Webb, this process could only be assumed. Scientists knew electrons must cool, but they had no direct measurements of how fast it happened or how strong the magnetic fields had to be. Without that information, it was impossible to determine which physical mechanisms were truly responsible for triggering the flares. Webb changed everything. By capturing the flare across multiple mid-infrared wavelengths at the same time, it allowed astronomers to watch the transition directly. from the hottest electrons to a cooler, evolving population. The shape of the spectrum revealed how energy was distributed, how quickly it was lost, and how magnetic fields controlled the process. The strange fade of a black hole flare. Every flare from Sagittarius A star begins with a sharp rise in brightness as high-energy electrons emit intense near-infrared radiation. But what happens immediately after that peak has always been the most puzzling phase. Observers would watch the flare fade, but the fading didn't follow a simple rule. Sometimes it dropped rapidly, other times it lingered, sometimes the color changed, sometimes it didn't. Without mid-infrared data, no one could see the underlying physics. Webb provided that missing clarity. By observing the flare across multiple mid-infrared wavelengths at the exact same moment, astronomers could finally track how emission changed as electrons cooled. This cooling, driven by synchrotron radiation, turned out to be one of the most important fingerprints of what is truly happening near the black hole. For the first time, the life cycle of a flare, from birth to decay, could be observed as a continuous physical process rather than a collection of disconnected clues. High-energy electrons lose power by emitting radiation as they spiral around magnetic field lines. As their energy drains away, the wavelength of that radiation shifts, moving from shorter, hotter wavelengths to longer, cooler ones. In the James Webb Space Telescope's observations, this shift was impossible to miss. The flare didn't simply fade, it evolved. Its spectral shape changed over time. The spectral index, which describes how brightness is distributed across different wavelengths, steadily transformed. At the start of the flare, emission was dominated by the highest energy electrons, producing a steep, bright spectral curve. As time passed, that curve flattened and shifted toward the mid-infrared. This was a clear sign that the electrons were cooling, precisely as synchrotron theory predicts. This marked a major breakthrough. For decades, models had suggested that synchrotron cooling should occur around Sagittarius A star, but no telescope had ever been able to observe it directly. JWST's data showed that the fading of the flare was not random. It followed a precise, predictable pattern governed by the black hole's magnetic environment. Even more importantly, the rate at which the spectral index evolved provided something astronomers had never had before: a direct measurement of the electron cooling timescale near Sagittarius A star. Measuring the invisible force cooling timescales matter because they are directly linked to the strength of magnetic fields. Faster cooling means stronger magnetic fields. Slower cooling implies weaker ones. Before JWST, estimates of magnetic field strength near Sagittarius A varied wildly. The uncertainties were enormous. Now, for the first time, those values could be anchored to real observations. With synchrotron cooling confirmed in real time, astronomers could finally calculate the actual magnetic field strength in the region just outside the event horizon. This measurement is critical because nearly every theory explaining how flares form depends on magnetic fields. They guide electron motion, regulate energy release, and determine whether a flare becomes bright and explosive or faint and fleeting. Until now, there was no clean way to isolate magnetic effects from other factors, like electron density or temperature. Some models predicted strong, tightly wound magnetic fields. Others favored weaker, chaotic configurations. There was no definitive way to decide between them. JWST changed that. When electrons cool through synchrotron radiation, the rate at which they lose energy depends almost entirely on the magnetic field they move through. Stronger fields drain energy rapidly. Weaker fields allow electrons to radiate for longer periods. By tracking how the mid-infrared flare faded and how the spectral index evolved, astronomers could determine exactly how fast the electrons were cooling. That cooling rate translated directly into a measurement of magnetic field. That's without relying on guesswork or adjustable model parameters. This was especially important because previous estimates based on near-infrared data were plagued by uncertainties about how many electrons were involved and how their energies were distributed. The mid-infrared measurements avoided those complications entirely. They provided a clean, physics-driven constraint. For the first time, astronomers had a reliable number describing the environment just outside Sagittarius A times event horizon. The results showed that the magnetic field near the black hole is strong enough to shape the motion of plasma and influence the structure of the accretion flow. They also support the idea that magnetic reconnection, the sudden snapping and rejoining of magnetic field lines, is likely responsible for triggering the flares. When reconnection occurs, enormous amounts of energy are released in a tiny region, accelerating electrons and igniting the outburst. The telescope that made it possible. When astronomers look back on this discovery years from now, they will likely agree on one thing. It could only have happened because of the James Webb Space Telescope's unique design. This wasn't a modest upgrade to existing observatories. It was an entirely different way of observing the universe. Everything about JWST was engineered around a single challenge: detecting light that is both incredibly faint and incredibly cold. Mid-infrared wavelengths are extremely sensitive to heat. Even a small amount of thermal noise from the telescope itself would completely overwhelm the signal from Sagittarius A star. That is why JWST operates at temperatures near absolute zero, shielded by a massive 5-layer sun shield that blocks heat from the sun, Earth, and Moon. Its instruments sit in an environment colder than anything naturally found on Earth. Without that extreme thermal control, the mid-infrared flare would have vanished into noise. At the heart of this capability is JWST's mid-infrared instrument, or MIRI. But it wasn't just MIRI's sensitivity that mattered. The decisive factor was its medium-resolution spectrometer mode. Instead of recording a single brightness value, the spectrometer spread the flare's light across multiple mid-infrared wavelengths simultaneously. This allowed astronomers to track the flare as it brightened and faded, watching how its spectral shape evolved across the entire mid-infrared range. That capability was unprecedented, and with it, a long-standing mystery at the center of our galaxy finally came into focus. No previous space telescope had ever combined this level of sensitivity with broad mid-infrared coverage. The Spitzer Space Telescope could observe portions of the mid-infrared spectrum, but it lacked the resolution and speed needed to capture rapidly changing events like black hole flares. Ground-based telescopes never stood a chance. Earth's atmosphere blocks nearly all mid-infrared light, making such observations impossible from the surface. But it wasn't just the technology that mattered. Timing mattered too. Sagittarius A splashed without warning. Catching one during JWST's observation window required careful planning and a measure of luck. When the flare occurred, JWST was already watching, recording the event across 4 mid-infrared wavelengths simultaneously. As the flare rose and faded, the telescope captured every phase. This was not a single image. It was a complete multi-wavelength timeline of energy moving through the environment of a supermassive black hole. A new map of the galactic center, with the mid-infrared flare captured in unprecedented detail. Astronomers were able to assemble the most complete picture ever created of the region surrounding Sagittarius A star. For the first time, a flare could be traced from its initial burst in the near-infrared, through its cooling phase in the mid-infrared, and into the slower variability observed at radio wavelengths. Each part of the spectrum filled in a different piece of the puzzle. Together, the data revealed a layered dynamic structure near the black hole, one shaped by extreme gravity, intense magnetic fields, and fast-moving plasma. The combined observations confirmed that these flares originate extremely close to the event horizon, within just a few Schwarzschild radii. At that distance, space-time itself is severely warped. Electrons producing the flare are not only guided by magnetic fields, they are moving through a region where gravity bends space and time. Their trajectories curve, their energies change rapidly, and their radiation responds on timescales of minutes. In such an extreme environment, even small shifts in magnetic structure or plasma motion can trigger sudden, dramatic bursts of energy. A turbulent magnetic environment. Another key insight came from the structure of the accretion flow itself. The gas surrounding Sagittarius A is not smooth or uniform. Instead, it is patchy, turbulent, and dominated by magnetic forces, rather than gravity alone. While theoretical models had long predicted this behavior, the mid-infrared data provided direct evidence. The environment is governed by fast-moving electrons, intermittent magnetic reconnection events, and rapidly shifting magnetic fields. This supports the picture of Sagittarius A as a low accretion rate black hole, where magnetic processes, not steady infall of matter, drive its activity. The spectral evolution of the flare further refined models of particle acceleration. The observed cooling curve closely matched predictions from synchrotron theory, strongly indicating that magnetic reconnection is the primary engine behind these flares. In other words, the energy released is not coming from matter falling into the black hole. It comes from magnetic fields snapping, reconnecting, and converting stored magnetic energy into particle motion and radiation. Seeing the unseen taken together, the near-infrared, mid-infrared, and radio observations formed a coherent picture for the first time. Not just a map of space near the black hole, but a map of the physical processes shaping it, a map created from light that had never been observed before. With the James Webb Space Telescope, astronomers didn't just see Sagittarius A a point more clearly. They uncovered the mechanisms that power its hidden activity, revealing how even the quietest black holes can briefly flare to life. And this is only the beginning. Let us know your thoughts in the comments below.